Lovely to see so many of you come for the intermediate black holes, obviously, and then followed by stargazing. Plan for the evening is talk from our very wonderful headline speaker, and then we'll lead you out onto the lawn for stargazing. And I'll explain a bit how that works at the end of the talk, just so we can crack on with the main event. So we're here with Antti Ranala, who's been studying these intermediate black holes, these very fascinating black holes that we're still trying to understand. I'm sure he will tell you all about them. Antti.
Okay, good evening everyone from my side as well. So today I'm going to explain you about what are the intermediate mass black holes and why they might be actually the most interesting type of black hole of all. Of course, obviously, intermediate mass black holes are black holes, hence their name. And black holes, of course, they come from the mathematical theory of general relativity, which was formulated by Einstein over 100 years ago. Black holes overall, of course, are characterized by their masses, their spins, how they rotate, and also the electric charge, even though this is not very relevant for astrophysical black holes. Astronomical observers have observed black holes since the 60s, so about 65 years now, so this is not exactly new. And we now understand how black holes, how they grow. About their formation, that's still uncertain, I'll talk about it, but their growth is quite well understood. Black holes can grow by eating gas. They eat gas, they get more massive. They can disrupt stars that wander too close to the black hole. And they can also grow by merging with other black holes, forming a bigger black hole. Of course, then what are intermediate mass black holes? They are typically introduced like a little bit counterintuitively of like what they are not. So intermediate mass black holes are not small black holes, and they are not big black holes, but they are something in between. So essentially, they are not stellar mass black holes, which are a little bit better understood, that form as an end product of evolution and life of massive stars. They are not supermassive black holes, which we find to inhabit the centers of massive galaxies. So these are something in between. Of course, when we look how stars evolve, a low mass star like our sun will live a very, very long time, billions and billions of years, until evolving into a red giant star, a very large one, and then evolving into this final stage of planetary nebula and leaving a little remnant behind. So this is for low mass stars. But what happens for like very, very big and bright and hot stars, such as this blue supergiant here? Their lifetimes are shorter. They explode at the end of their lives, leaving a remnant behind. In the case of the most massive stars, a black hole. So stellar mass black holes originate from the lives of massive stars. How we can actually observe them? Of course, a black hole is black. If it sits in the middle of an empty space, it's very difficult to observe those. But many black holes are a part of like binary systems. They are orbited by other stars because they were not born alone. If a black hole forms in this type of a system, it might eat gas from the companion star, and we see this bright accretion signature from this type of a feeding event. Now let's go to much, much larger scales. Stars are very small, light seconds in size, very, very, very small. Galaxies, on the other hand, are tens of thousands of light years in diameter. This resembles the spiral galaxy we live in, the Milky Way. This is, of course, not the Milky Way because we are sitting inside our own galaxy and we cannot get images of like that from our own home galaxy. Each massive galaxy hosts most often a single supermassive black hole at their center. And even though these supermassive black holes, by their name, are supermassive, like by spatial dimensions, they are very small. So we cannot see black holes looking at galaxy images, like seeing a black dot at the center, I mean. But of course, for example, if the black hole at the center of the galaxy eats gas, this accretion signature results in the emission of light, X-rays, or radio waves, and this is why astronomers spotted these massive black holes at the centers of galaxies, in the first place over 60 years ago. Of course, due to technological advances, mainly thanks to radio interferometry, we can now, or the observers can actually take images of the shadows of the black holes. So this is a real radio image of a shadow of the black hole. So the red bright torus here is the radio emission from the hot plasma around the supermassive black hole in a massive galaxy M87. I will show the picture of the galaxy later. And the shadow of the black hole is the the black dot at the center here. So the shadow, in itself, it's not the event horizon of the black hole inside which nothing can escape. The horizon, this like shadow is a couple of times larger. So the shadow is of the size of this, and the actual black hole is a little bit smaller in this galaxy. Okay, here is how the host galaxy of this black hole looks like. So we can clearly see the orange-yellow component of the old stars of this galaxy, but we can also see the curios like this jet originating from the center of the galaxy, and that is the signature of the black hole feeding at the center of this galaxy. And there you cannot see it by eye. Of course, this is an optical image taken with Hubble Space Telescope, and here I just show like how small this like radio interferometric image of the black hole would be at the center of this very massive galaxy. Of course, our Milky Way galaxy also hosts a supermassive black hole at its center. As I mentioned, this is not a Milky Way, but a Milky Way-like spiral galaxy. Like the galaxies come in two basic types, like these ellipticals and these spirals. So since the 90s, people, most prominently two research groups in Germany and in the US, have actually observed in infrared wavelengths how do stars move at the center of the Milky Way. There is a known radio source called the Sagittarius A star. The star is a little bit of a misnomer because it's not a star, it's a black hole, but that's how they call it in the radio catalog, hence the name. People have monitored how these stars move, and they are making orbits at the center of something, nothing in empty space. So that's where the black hole is, at the center of our galaxy. And independently, the shadow of this black hole has just recently, a couple of years ago, imaged. So this is like independent evidence of the black hole at its center. Of course, now we come to the big puzzle. We know where stellar mass black holes come from. They come from massive stars. But no one knows where supermassive black holes came from. How did they originate? We know how they grow. They eat gas, they might eat stars, they might merge with each other. But what was the starting point of this merging cascade, this merger process, this gas-eating process? No one knows what was the seed of the black hole. What was the starting point of the process? That remains unknown at the moment. People launched the James Webb Space Telescope. Maybe this helps with the black hole puzzle. No, during recent years, the puzzle has been only made more puzzling. And this is because using the James Webb Space Telescope, observers, also here in Cambridge, they have found black holes farther and farther away in the early universe. Essentially, black holes with over a million solar masses have been discovered when the universe was only a fraction, a few percent of its current age. So that means that this rapid emergence of these black holes strongly suggests that the stellar black holes cannot be the progenitors, the starting point of this black hole seeding, because the black holes simply do not have enough time to grow into these monstrous mass scales if they start from little stellar black holes. Okay. Let's look at the black hole mass landscape a little bit better. So small objects are on the left, and massive objects are on the right, from 1 to 1 billion on this scale. We start with the sun, which is not a black hole, because the sun is a star, but this is just for scale. Then we have stellar black holes of masses about from 5 to 50 solar masses, so still like manageable scales. A couple of times more massive than the sun. Then, on the other hand, I showed you the supermassive black holes, which have masses ranging from about 4 million in the case of our galaxy, and 6 billion in the case of this massive black hole in the elliptical bright red galaxy M87. And as you can see, there is a gap in the middle. And this is where the name intermediate mass black holes come from. So in the universe, we can observe the stellar mass black holes, and on the other hand, we can observe the supermassive black holes. But there is clearly this sort of a like gap in the mass of the black holes that can exist. This is related to the origin puzzle of the supermassive black holes, because of course, how did we get here? We know that surely these stellar black holes on the left, they surely exist, but are these the progenitors of these? So essentially the question is, can you start stellar and then grow supermassive? Of course, the intermediate mass black holes, if they can somehow form, might help us with the puzzle, because you can start intermediate and get a head start in this competition of growth. So because you have a head start, you need less time to grow, and maybe you can then explain how these black holes got so massive. People have thrown lots of theoretical, sometimes speculative ideas what could be the origin of these black holes. For example, they might be collapsing gas clouds in the early universe. Nowadays, in the present day universe, if you collapse a gas cloud, you form a cluster of stars. But the chemical composition was different in the early universe, and it's possible that under certain conditions you could actually form a black hole from a gas cloud. Of course, we know that black holes form from stars. What if in very dense star clusters, stars can collide, and you can build up more massive stars with colliding less massive stars? That also gives you a head start for the black hole mass. Then there are a little bit more speculative ideas that maybe these black holes could be primordial and originate from the first second of the Big Bang. But this belongs to the realm of particle physics rather than astrophysics. This is the stellar collision scenario is something I have a little bit worked on, so I will show one slide out of that. So essentially, how do I study the stellar collision origin of massive black holes in this type of star cluster setups? So how I do is using computer simulations. So this is just an example of a large computing cluster with GPUs, some code and math over there. But what the end product is, I can form these like very nice diagrams how this type of collision cascades can form the black hole. Time flows from the top to the bottom. First, stars in binary stars collide because they have large interaction cross-sections while they orbit each other. The cascade builds up. I collide and collide and collide the stars. This happens while solving the equations. And finally, I have built a star which is few thousand solar masses, so few thousand times the mass of the sun. And these are stars that cannot form alone. These are too massive for that. But essentially what the end product is, I get these like head start black holes with masses of few thousand solar masses right into the realm of intermediate mass black holes. Okay, so 1,000 to 10,000 solar masses, that's where the intermediate mass black holes should be. But okay, some of them might have grown into this million solar mass, billion solar mass, supermassive range. But it is not guaranteed that every black hole seed would grow. So essentially, some of the black holes would retain their original mass throughout the ages of the universe. Then there comes some important point. One cannot destroy an intermediate mass black hole on an astrophysical timescale. Like a black hole might evaporate over cosmological timescales by Hawking radiation, but that would take like lots and lots, like many times of the age of the universe. So essentially, like if an intermediate mass black hole formed in the early universe and didn't grow, it should be here present in the local universe. This gives us very interesting prospects. That means that if we actually can find an intermediate mass black hole or a population of them in our Milky Way galaxy, and understand their masses and properties, maybe we can say which of this formation process for the supermassive black holes is true. So we can study the very early universe here today in the local galaxy at home. So maybe the intermediate mass black holes then could provide us a way to actually solve this very puzzling black hole origin conundrum. Okay, how to look for an intermediate mass black hole? So if astronomers want to search for them, like what is the place where to start? So astronomers have checked in which kind of galaxies these massive central black holes like to live. And they have established these empirical correlations. For example, here, this diagram showing that more massive black holes like to live in more massive galaxies. And on the other hand, the opposite is also true. Less massive black holes like to live in less massive galaxies. So if we want to search intermediate black holes and not supermassive black ones, we should focus on star systems that are smaller than galaxies. Essentially, this means that star clusters might be very important places in these searches for intermediate mass black holes. So essentially, this means that, for example, a globular cluster, this is a simulated image from my work, but globular clusters of stars, which, for example, amateur astronomers and also professionals like to observe, these might be very good points to do these searches for intermediate mass black holes. The difficulty is that these clusters usually only contain stars. They do not contain any gas that the black hole could eat, so we cannot see the feeding signature of this black hole. Essentially, what it means that astronomers try to observe the gravitational effect of the black holes on the stellar orbits, because the black holes are so massive, they can perturb how stars move at the centers of these globular clusters. If the black hole is there, that's the yes. Unfortunately, this process is pretty difficult, and it has proven that it is very difficult to actually distinguish between one intermediate black hole in a star cluster compared to a collection of ordinary stellar black holes. We know that, the cluster consists of stars, so it also includes a collection of stellar black holes, which usually, unfortunately, tend to sink to the center due to their very high masses compared to the stars, and that's also where the intermediate black hole would be. So this is a difficulty. It's an open puzzle in modern astrophysics. Do globular clusters really contain intermediate black holes or just large collections of ordinary stellar black holes? Fortunately, there is one very good example where scientists can actually distinguish that there is an intermediate black hole and not a collection of stellar black holes. So this object is called the Omega Centauri. So this is a globular cluster-like object, a massive old star cluster which is orbiting the Milky Way. And during these times, it can be observed in the southern constellation of Centaurus, so probably not visible from here from Cambridge. This star cluster is the most massive of its kind around the Milky Way, and of course, consequently, it also consists of the largest numbers of stars compared to the other globular clusters. Studies have shown that maybe this object is not a star cluster at all. Maybe it is the central nucleus of an ancient dwarf galaxy that was consumed by the Milky Way. This is what the stellar population properties of this cluster have revealed us. But nonetheless, it is an ideal place for hunting for local intermediate mass black holes, especially because the scientists with the Hubble Space Telescope, they used this Omega Centauri star cluster as a calibration field. So essentially, this means that there are lots and lots of images of this cluster, and scientists can try to establish the orbits of the stars at the center, seeing from image to image taken over a time span of 20 years how do the stars move at the center. These searches have been actually pretty fruitful. This group of scientists in Germany, they released this paper 2 years ago showing that there is a collection of very fast-moving stars at the center of this globular cluster. So if you have a very fast-moving star, of course, this means that over a short period of time, you should fly away if you move very, very fast. But how can you move very fast and not fly away? The key thing is that the stars are actually orbiting something. They move very fast because they are revolving around the intermediate mass black hole at the center of Omega Centauri. And analysis have revealed that the mass of the object which these very fast stars are orbiting is about 10,000 solar masses, so right into the perfect range for an intermediate mass black hole. I mentioned earlier in the talk that this is how scientists 2 decades ago, they weighted the Milky Way center black hole by seeing how the stars are moving around the center of our galaxy. So essentially, this Omega Centauri black hole is a mini version of the Milky Way center. The Milky Way black hole is about 100 times more massive. So here you can compare how the Milky Way center looks like and how the Omega Centauri center looks like. So both of these star systems have very fast-moving stars revolving around a black hole at the center. So this Omega Centauri black hole is most likely the second most massive black hole in the Milky Way galaxy system after the central black hole, and this is thus far best evidence of the existence of intermediate mass black holes. Other evidence originates from gravitational waves and luminous X-ray objects, which I won't discuss further in this talk. Okay. We reached the end of my intermediate talk, and let me just summarize a few central concepts. Intermediate mass black holes fill the gap between the stellar black holes and the supermassive black holes, and they might provide us the solution to the supermassive black hole origin puzzle, given that if we can observe, find, and characterize their population in the Milky Way and in the local universe. Okay, that's it from my side. Thank you.
Okay, put the lights on a little bit so we can see you. Do we have any questions for our speaker? Right at the front, start us off, yeah.
So the stuff that gets sucked into the black holes, where does it all go?
It goes to increase the mass of the black hole. That's it. So
does the mass get converted to energy somehow or something in the mix?
well, like I showed these images of these jets coming from near the galaxies, but this is something that doesn't go inside the event horizon. So around the black hole, if it eats gas, there is something called the accretion disk. So from the galaxy, the gas goes to the accretion disk. A part of the material from the disk is eaten by the black hole. That disappears forever, and the rest is thrown about by complex interactions with magnetic fields and so on. So essentially, only a fraction of the material that goes near the black hole actually goes inside the black hole, and what goes there stays there, but the rest is thrown out.
Lovely, and we've got a question here.
About 10 billion. So that's like 1 and 10 zeros after that. So that's many suns.
Blows my mind. Yes.
Related to atmosphere and the heating thing, is the mass and the number of planetary and gas in the bulge related to the size of the black hole? Like, is there more food, we call planets and gas food, the black holes linked in?
Yes, this is very much related, but like why this is exactly the case is a little bit uncertain still at the moment. So it seems that you don't observe Massive black holes in small galaxies and small black holes in massive galaxies. So the key insight is that the black hole and the galaxy have somehow like grown together. This is just not one moment in time, like how much gas and star is there at the moment, but any previous times in the universe as well. So this is the coevolution. Astronomers are actively studying like why this is exactly the case, but these empirical correlations suggest that there is there is the link. Yes, yes, definitely.
Hand shooting at faster than I can cope with them. Yes, please.
How much does a black hole weigh? Sorry, no. What's a black hole made of? And if so, if they're made of gas, what kind of gas?
Black hole is made of like, if you take any material, like stellar material or gas with any composition, if you compress it enough, it will collapse into a black hole. After that, it stops being made of things, and it's essentially like a gravitational bottleneck. After that, it's just like pure geometry of space-time. So after its formation, the black hole actually is not made of any physical material. That is just like how space actually bends.
Okay, yes, please.
You showed a picture where the stars were orbiting close one. Yeah, could you explain that picture more? Because what's the time scale is what, 25 years?
Yes, so there is like one particular star, like maybe you can see the cross is the location of the black hole. Yeah. And there is this very famous star called S2. It was called S2 both in the American and the German catalogs, so it's called the S2. And it has an orbital period of like, is it 12 or 16 years. Yes, one can actually see the whole orbit. That is a very, very nice result. So.
Very fast for anything.
It starts to be a like measurable fraction of a speed of light, and people can observe that the orbit of this star is actually not perfect Keplerian or Newtonian, but you have to take like Einstein into account because you go so close to the black hole. You can really see it in the orbital speed. There is a deviation that only like relativity can explain.
It orbits around the point.
Yes, an empty point in space where the black hole is. Yes.
Okay, time for a couple more, maybe. Yes.
These primordial black holes that you mentioned, are they linked to dark matter?
Some people have suggested that, but at the moment this is still a very active work in progress, and there is no like a final conclusion whether this is true. Some people have proposed that maybe black holes are dark matter, or a fraction of dark matter could be tiny black holes. But whether these are stellar black holes or like elementary particle mass black holes, that's still an open question. And not all people, all scientists like believed in these theories. But of course, this is one of the models that are still plausible at the moment. So they haven't been like completely ruled out. That's my point of view.
It's time for a couple more, maybe. Who shall we pick? Yes, go on then.
What is a ultramassive black hole?
What's an ultramassive black hole?
Ultramassive black hole is typically scientists, when they like to say that we have found the biggest thing ever, they like ultra high, like super is small for them, like they have ultramassive black holes, hypermassive black holes. So typically one would call a hyper or ultramassive black hole something that is over 10 billion solar masses. Like a supermassive is only million to billion, but when you go to 10 billion, then you are ultra or hypermassive.
Okay, let's do, you've been very patient. We'll do the last question here in the middle, please.
Aren't there supposed to be 3 types of black holes? The ones you mentioned
Are there 3 kinds of black holes? It might mean stellar, intermediate.
In the terms of like, if you think like how massive the black holes is, then yes. So this characterization only comes from the fact that we know that there are stellar black holes, we know that there are supermassive black holes, and the intermediate mass ones would be in the middle. There might be like a fourth type of black holes from like these like primordial early universe sources, like these particle physics black holes. But this would be less massive than the stellar black holes. So that might be the hypothetical fourth type of black hole. But no one knows whether these exist. So 3 or maybe 4.
Wonderful. Okay, so first of all, we're going to leave you outside for the stargazing. Little bit of housekeeping. So for anyone that's not been here before, what you're going to see, you're going to be on the lawns